I'm Jordan Johnston,
And I'm Thomas Bradshaw.
and our project was a musical Tesla coil. So we'll go over first the circuit design for the Tesla coil, and then we'll go over the physical design. So how the Tesla coil works here is we have our circuit diagram. It's called a Slayer exciter circuit. And what happens is you have your voltage here at the top that comes through, and it goes into your transistor. And once this transistor base pin is bumped up, it'll open up the flow, allowing your voltage to come through our primary coil here. And once your voltage is coming through your primary coil, you then have a transformer that's created between your primary coil and your secondary coil, which boosts your voltage up high, and it also, on the other side, it makes your voltage go low. So you'll see that this wire is connected back to the base, and so what it does is your voltage from here is going high on your base, and your voltage from here is going low, and so it's creating a switching circuit with your transistor. Also, something to notice is over here that when the voltage goes high, it comes over to your capacitor, and the capacitor on this top plate is what's called the top load on our Tesla coil. So now we'll take a look at our Tesla coil here. So like we talked about on the circuit diagram, this would be your primary coil, this is your secondary coil, and this would be your top load. And what happens is once the voltage comes in here, it goes through your primary coil into your second coil where it gets ramped up. And once it comes to the top load acts as one plate of a capacitor. And the other plate would be the ground, or whatever the lightning bolt coming off of this plate is. And your dielectric is just the air in the room. And Thomas will talk a little bit more about how we made it musical.
So, using the Slayer exciter circuit, we were able to build the Tesla coil and test it and find its resonant frequency, the frequency it likes to switch back and forth at. And using that frequency, we then designed this circuit. This circuit, quite simply, interfaces our Tesla coil, seen here. Here's our secondary coil, our top load, and here's our primary coil. And here's the transistor to turn it on and off. But instead of having a loop back feature to turn it on and off, we use a microcontroller that takes in a audio signal through ADC and outputs a pulse width modulate signal through to turn on and off the transistor. And what this does is basically we're taking a typical audio signal, which is a very, more of a kind of sinusoidal sort of signal, and change it to a square wave with the pulse modulating in order to create the same music, but this can then, the time of each of these pulses can be at the frequency of the natural frequency of the coil, which allows us to have max power transfer and to create the sound. And now we're going to show you an example. We set up this circuit that I just demonstrated, and we've also put a speaker to show the same output. Because the one problem with our circuit is it requires high power, so high current and high voltage, which we are not set up currently to be able to produce. If we did have that, we'd be able to produce over here on the coil enough power to create sparks, but we don't have that. But we can show you how it would work if we did have enough. So when we play the music, we'll be playing Mario Bros. So, as you can hear from the music, it works. And to come over here, if you look at the oscilloscope, this is looking at the output at the music, okay, which will be the pulse width modulated waveform described earlier. Now, if we probe, if we probe the top load, we will see that it will be resonating according to the frequency. It will be resonating with the music. So the yellow line is the probe at the top load, which shows that this circuit will work. And hopefully when we ramp up the power, we should get sparks.